I'd like to begin today with a follow-up of our discussion of the Endangered Species Act and talk about causes of extinction, some of the characteristics that we see in animals that can put them at risk of becoming extinct, or at least ending up on the endangered species list. And usually just a couple of these are enough to put an animal on the endangered species list. So first of all, being high in the trophic level. So feeding high in the food chain basically puts an animal at risk, because the more steps there are in the food chain, the more possibility of disruption in the food chain. And of course, the higher you are in the food chain, the less energy available you have to you as well. So generally speaking, again, when humans especially come into ecosystems, usually the higher end predators are the ones that tend to disappear first. Also, being physically large, just being of a large size tends to put you at risk of extinction, because for one, you're big, you're easy to see. So if we're trying to find you, if we humans are trying to hunt you or find you, you're easy to find. Also, you need a lot of food, typically. So again, if there's disruption in the food chain, that puts you at risk. And then also that actually relates to the next one, is that the bigger you are, the slower you reproduce. So again, if there's a crash in your population, you're going to recover much more slowly. So again, that does transition into the next characteristic, which puts species at risk, and that would be a low or slow reproductive rate. So again, big animals typically reproduce slowly. And again, things like blue whale, elephant, and so on, but even things like elk as well, only will produce 1 or 2 calves a year. And again, a lot of times they will, as related to that as well, is they may actually have long lifespans, especially something like the blue whale, and so they may not be reproducing until they get into 10 or 20 years down the line. So another characteristic would be having limited or specialized breeding or nesting grounds. So for example, there are certain species of seabirds where virtually all of the members of the species actually will congregate on certain islands during their breeding times. And if something were to happen to those islands, basically you can wipe out the whole species. Another example would be bats. There's a cave called Bracken Cave that's pretty close to Austin, Texas. And in the summers, there's a breeding colony of bats that forms there that's 40 million bats, 40 million Mexican free-tailed bats. So again, if something were to happen to that one cave in the summer, you could pretty much not wipe out the species necessarily, but you'd put a big dent in the population in that area. Also having fixed migratory patterns. Waterfowl, who basically are moving north or south, depending on the time of the year. This also be true of the great whales. Basically, they're going to be in certain places at certain times of the year. And of course, we humans then can just sit and wait for them to come. Also having specialized feeding habits. The black-footed ferret I've mentioned a couple of times feeds only on prairie dogs. So again, something happens to prairie dogs, bad things are going to happen to them. What I generally consider to be unhealthy behaviors, and there are a number of these. Some of that could be aggression towards humans, but just other things as well. The key deer, for example, is a small deer in Florida in the Everglades, and it tends to forage along roadsides because they have become addicted to nicotine. So they actually forage for cigarette butts along roadsides, and so they have a high mortality from vehicular manslaughter, if you will, except it's deer slaughter in this case. So anyway, but they get killed in collisions with cars. The Carolina parakeet, which actually is extinct, had an odd behavior in that if a member of the flock was injured in some way, other members of the flock would hover around it. So basically a hunter could kill just one bird, and that would keep the rest of the flock nearby, and then they could literally shoot until their barrels melted. Continuing this, just being intolerant of humans, and again, this can take different forms. Something like a grizzly bear, which potentially could attack and kill humans, is one type of intolerance. But another example here in North America would be the Rocky Mountain bighorn sheep. Again, they just don't like humans nearby, and so they'll try to move away from humans. Humans can affect their overall health, maybe increasing the incidence of disease. Also, it can affect breeding behavior. So again, general intolerance can put species at risk. Having a valuable part, valuable fur, other parts as well. Rhinoceros horn is used as an aphrodisiac in Asian medicine, and so anyway, it's valued for that. The bear gallbladder is valued in Asian medicine, so that puts them at risk. So again, having valuable parts gives you an economic value, and we humans are going to go after you and kill you. If you prey on livestock, again, that's going to affect our bottom line economically, and so we are going to kill you. Having a limited distribution, again, something like if you look at an archipelago like the Galapagos, there are certain tortoises that you find only on certain islands of the Galapagos. So again, if something were to happen to that ecosystem, you could lose the entire species. Also, other things, such as, these aren't really characteristics of species in particular, but just building roads actually is hazardous to species because then it creates access for humans. Anyway, that potentially is a problem. And also roadkill is problematic. On a drive from San Diego to Sacramento a couple of years ago, it was unbelievable, but I kept seeing barn owls, dead in the road. And I ended up counting I started counting as I got into the Central Valley as I was heading north, and I stopped counting at 40. So just in a relatively short period of time, I'd counted 40 barn owls that were killed, flying, into vehicles. So anyway, I don't know what the reason for that was, but it was pretty amazing. Also, climate change, which we'll be talking about a little bit later, is also really not an animal characteristic, but it's certainly something that's putting a lot of animals at risk, something that they really can't control. And then, of all of these characteristics which put species at risk of extinction, really the primary cause of extinction globally is loss of habitat. Especially in the tropics, as we burn the forests and so on, we're just losing species that we never even knew existed, quite honestly, because we're losing forests faster than we can get in and find out even what's there. But again, of all of these characteristics, loss of habitat is the primary cause of extinction globally. All right, now I would also like to talk about a few global problems, a couple of global problems anyway, that affect species in general, but also have implications for we humans as well. And the first of these is ozone depletion. And ozone is a form of oxygen, so-called triatomic oxygen. And ozone is actually a pollutant in lower elevations, but in the upper atmosphere, it serves a role in that it can actually absorb ultraviolet radiation. So as ultraviolet radiation strikes the Earth or comes to the Earth, some of that ultraviolet radiation is absorbed by the ozone layer. And there are actually a couple of ozone layers in the upper atmosphere. So again, this is important because, again, if you had maximum radiation reaching the planet, this is potentially deadly to animals. So another thing to know about ozone is this, that as we lose ozone, it's not a 1-to-1 ratio with an increased ultraviolet radiation. So by that I mean if you have a 1% decrease in ozone, that translates to a greater than 1% increase in ultraviolet radiation. And it kind of depends at what altitude you are at and what latitude you're at as to how much that will of an increase that will be. But again, the point is that there'll be a greater increase in UV radiation for each 1% decrease in ozone. Now, ozone depletion is primarily a problem in the Antarctic region, or at least it was initially discovered there, although ozone holes have formed in the northern hemisphere as well. And so, back in the 1980s, it was observed that there was actually a loss of ozone occurring in the southern hemisphere. And at first it was not known if this was just something that had always occurred but we had never noticed, or whether this was a new phenomenon. And by looking at atmospheric records from the previous years, they determined that this was a new phenomenon. And as you can see, looking comparing 1979 to 2006, the bluer it is, the darker it is, basically the greater the loss of ozone. So you can see that ozone hole is bigger and deeper and darker than it was 20 or 30 years ago. So this is a real phenomenon. And essentially the cause, and we'll talk about some of the gases in a second, are chlorofluorocarbons are the primary cause, but the biggest depleter here is chlorine and some of the related compounds. Bromine also would be a problem. And basically what chlorine will do is that it will react with ozone, and it will go through a series of reactions that really eventually re-release that chlorine so that it can destroy more ozone. So the problem then is chlorine accumulating in the upper atmosphere, as well as some of the other halogen gases like bromine. They'll also react with ozone. So as we look at the ozone depleting gases, one of the biggest culprits are what are known as CFCs, chlorofluorocarbons. And CFCs have been used as refrigerants. They also are used in industrial applications, like, as in the production of styrofoam. And those would probably be and also they're used as aerosols and aerosol cans for a long time as well. And so anyway, they're fairly non-reactive, they're fairly inert, and that's really their value. But as it turns out, when they get to the upper atmosphere, and and particularly in the Antarctic, what happens there is that the CFCs actually condense on crystals, ice crystals in the upper atmosphere. And then they get in fairly high concentrations. They actually can react with ultraviolet light to release the chlorine. So anyway, they also tend to have a long life in the atmosphere as well. So again, as we look at the chlorine in the upper atmosphere in terms of human causes, CFCs have been one of these problems. And so it was predicted that CFCs could destroy ozone, I think back in about the 1950s, but no one really thought that the conditions could exist in the upper atmosphere for them to do that until we started finding the ozone holes in the Antarctic. So anyway, the primary culprit then are CFCs. And fortunately, over the last 20 years or so, nations have tried to find alternatives to CFCs, which I'll get to in a second, and this has helped stabilize the loss of ozone. Other ozone destroyers would include other halogens, fluorine or chlorine relatives, which would include bromine and bromides. And bromides are used in a lot of different industrial applications, but also there are some important insecticides, fungicides, that contain bromine. And eventually, again, the bromine will work its way up to the upper atmosphere and kind of do the same thing that fluorine will. Carbon tetrachloride is another, again, it's basically an industrial type solvent, as is methylchloroform. And then HCFCs are a relative of the chlorofluorocarbons, basically used as refrigerants and taking the place of CFCs. And they are less harmful to the ozone layer than are CFCs, although again, you can see they do have some capacity to destroy ozone. So again, I guess part of the good news about the ozone layer is that even though we have had a pretty dramatic loss here, as you can see, since the 1950s, it appears that over the last decade or so that loss is beginning to level out. So we don't know if that's going to recover or not, but at least we think we've seen the bottom here. And again, looking at consequences, because another question you might say, well, who cares really whether there is an ozone layer or not? Again, as I mentioned, ultraviolet radiation can have consequences. It certainly contributes to skin cancer and in us. And the biggest problem too is that there are natural causes of chlorine in the atmosphere as well. So an example would be volcanic eruptions. So again, if you've already got high levels of ozone destruction and then you compound that with natural causes of ozone destruction, then you can really get sometimes very intense ultraviolet radiation showing up. And again, ultraviolet radiation then, again, in animals can cause cancer. It's also considered a suspect in the amphibian population decline that we're seeing. Global warming probably contributes to that, but also ozone depletion. And then also, again, plants, themselves, of course, they need solar energy, but high levels of UV radiation actually can kill plants as well. And again, as we look ahead to global warming and potential losses of food supply, we need to maximize food supply, and the last thing we need is plants dying from ultraviolet exposure. So again, while there is still a lot of concern about ozone depletion, again, we are seeing a trend where we think we've seen the worst of it, and as long as it doesn't get any worse, hopefully we'll be okay, as will other species. But again, it may be impacting some species, particularly amphibians. Now, the other global problem, which is really significant, is greenhouse warming. And again, potentially serious for all species on the planet, including ourselves. And so I want to talk a little bit about this, and hopefully you have some experience with this. So the term greenhouse warming refers to the kind of effects that we see in greenhouse. And as you probably know, greenhouses are composed of glass or plastic. And so what happens in these situations is that solar energy, when it strikes a greenhouse, some of that energy is reflected by the glass or plastic, but some of the energy penetrates the glass or the plastic and gets inside the greenhouse. And when that happens, as the light passes through the glass, it will change the wavelength of the light, so it alters the wavelength. And so instead of that energy then being able to radiate out as easily as it penetrated the glass, it will not be able to penetrate the glass as easily when the wavelength lengthens. So energy will enter the greenhouse faster than it radiates out of the greenhouse. So energy accumulates within the greenhouse and the greenhouse warms. So again, it's all about just solar radiation, absorbing the energy faster than it can be radiated out. And that's what leads to the accumulation of temperature. Now, as we look at the Earth, essentially we have the same kind of effect going on in that we have the atmosphere surrounding the planet. And so solar energy can strike the upper atmosphere, and just as in the greenhouse we talked about, some of that energy is reflected. And we refer to that reflected energy as Earth's albedo. And so, approximately a third of the energy that reaches the upper atmosphere is reflected. And so it's going to be reflected by, water particles, clouds, potentially dust in the upper atmosphere as well. Some of that dust will absorb that energy. Some of that dust potentially reflects some of that energy. So again, Earth's albedo then would be the reflected light that's striking the upper atmosphere. Now, the other possibility here as well is that solar energy then is absorbed by the atmosphere or by the oceans or by the surface of the Earth or by the plants and other producers. And eventually that energy will be processed through food chains and other things like that. But eventually it's going to radiate back into space. And that's known as Earth's emissivity. So again, about a third of the energy is reflected. That's the albedo. The other 2/3 is absorbed and eventually irradiated back into space, and that's known as Earth's emissivity. So I think you can see then that changes in albedo or changes in emissivity, the rate at which energy is being released back into space, can affect global temperatures, because that will affect total energy in the system, and that can affect global temperature. So let's see what kind of changes potentially could occur and what the effect would be. So starting with albedo. So if we have a certain amount of albedo, let's say that albedo increased. So instead of a third of the energy being reflected, maybe half the energy striking the Earth is reflected. So if we increase albedo, what would be the downstream effect? Well, that would mean less energy being absorbed by the planet, and so that would lead to a net cooling effect on the planet. Now, what if albedo decreased? So instead of a third of the energy is being reflected, only a quarter, or a fifth, or something like that is being reflected. That would mean then that more energy is actually being absorbed by the planet. And if emissivity, and again, in both these cases, we're assuming emissivity doesn't change, but if emissivity doesn't change, then total energy would increase. That would lead to warming of the planet. Additionally, if we look at emissivity then, if you increase emissivity, increase the rate at which energy is being lost from the planet without changing albedo, that's going to lead to a loss of total energy, and that would cool the planet. And again, if you decreased emissivity so that energy is being released more slowly than it had been previously, energy would accumulate, and that would lead to warming. So when we look at greenhouse warming, so-called greenhouse warming, this is what is happening. Basically, emissivity is being decreased because it is the mixture of atmospheric gases then that can affect how slowly or rapidly energy is being released back into space. And again, by reducing emissivity, that leads to an increase in energy, warming of the planet. So what are some of the greenhouse gases? So what are some of the gases in the atmosphere that contribute to holding the energy longer and leading to a warming of the planet? As it turns out, actually, the strongest greenhouse gas is actually water vapor. And I'm also going to have a comment about human contributions to this greenhouse warming. So water vapor is a strong greenhouse gas. Now, again, it's a little complicated because water vapor also can condense on particles in the atmosphere, producing water droplets, which can also contribute to albedo, reflecting that light. But water vapor itself, as we've talked about before, water tends to hold energy and release energy more slowly than other compounds. So again, it contributes to warming. Now, in terms of human production, carbon dioxide is one of the things, gases that we're producing that is a greenhouse gas. And so carbon dioxide is another greenhouse gas, and it's a powerful greenhouse gas. Even though carbon dioxide makes up a tiny fraction of the atmosphere, again, it is powerful in terms of its influence. Another significant greenhouse gas is methane. It's actually even a stronger greenhouse gas than carbon dioxide if you did it per gram, but it or by weight. But there's less methane in the atmosphere than carbon dioxide. So right now, at least, it has less of an effect. Other greenhouse gases, I think, that are of lesser importance: nitrous oxide, ozone, and CFCs also contribute. But I don't want to confuse the issues here in that really here the big two of really interest to us are going to be carbon dioxide and methane. Again, water vapor is significant as well, but we're going to talk mostly about carbon dioxide and methane. Okay, so as we look then at the relationship between carbon dioxide and global warming, as you can see here, this kind of staccato line going up is looking at carbon dioxide as measured in Hawaii. And you can see that over the last several decades that carbon dioxide has risen, and global temperature. Average temperature is rising with it. And again, the undulating line here related to carbon dioxide has to do with carbon levels changing with the seasons. So, as photosynthesis increases in the summer, it's going to pull carbon out of the atmosphere, and then in the winter, when there's less sunlight and so on, carbon will be released, or less carbon will be absorbed, however you want to look at it. So again, that's what we're seeing here, and then again, global temperature is the red line here, and it's growing with that. So again, part of the debate, if you go back into the 1960s and early 70s, is was this a coincidence or is this a cause and effect relationship? And that's always one of the issues that we have. And could it be other causes besides just greenhouse gases? Could this be part of a natural cycle and that the greenhouse gases are just coincidental to this? Well, again, there are a few things that we'll talk about here. So again, we can look at greenhouse effect versus solar warming, which would just be due to the effect of a greater irradiation of solar energy. And as we look at, and part of the argument here that supports greenhouse gases is that the type of warming that we're seeing is consistent with a greenhouse effect and not so much with an increase in solar energy. For one, even though we're seeing more solar flare activity and so on, in terms of direct measurements of solar energy, we're not really measuring a dramatic boost or a boost of solar energy, whereas we are seeing a dramatic increase in the greenhouse gases. So again, and also when you look at the type of warming that we're seeing, again, if we look at the equatorial regions, the tropics, warming there is not that great. Where the Earth is really warming more significantly is in the temperate and polar regions. And so that, again, is more consistent type of warming and a more predicted type of warming that we would see with greenhouse gases as opposed to an increase in solar radiation. And again, there's other lines of evidence as well, but that's a big part of it. Now, another thing I want to say too then is if we look at mitigating the effect of carbon, particularly carbon dioxide in the atmosphere, but we're basically talking about the carbon cycle. So if we look at how did we get here? How did we end up with all this carbon in the atmosphere? I mean, it's pretty straightforward. We basically have dug up all of these ancient forests that have existed the last 400 million years, and we've burned them in the form of fossil fuels, and we continue to do that. And we've also been cutting down and burning our surface forests. So the forests would normally be pulling that carbon out of the atmosphere, yet we've been burning those, which would further throw carbon in the atmosphere. Plus we've been, burning off all of these ancient forests. So again, it can't be a surprise then that carbon accumulates in the atmosphere. So again, if we want to mitigate this problem, we have to decrease the carbon going into the atmosphere and increase the ability to pull carbon out of the atmosphere. So as we look at concerns regarding global warming, they are many. And so one of these certainly is related to food supply. We've talked about population growth. We may very well be doubling population again in the next 70 years or so. And again, there's going to be dramatic climate changes going on, and they're hard to predict. And so one of the things certainly that's important is that, the reason that here in the United States that we do not suffer from poverty is that we are an affluent country. The primary cause of hunger globally is poverty. So we happen to be an affluent country, but we also have and experience some of the prime growing regions. The temperate grasslands in North America run right through the United States. That's a great thing. And with global warming, it's expected that those prime growing regions for grains, particularly wheat and corn and so on, are going to shift to the north. And so, Canada may become the breadbasket of the world instead of the United States. So again, this is an important thing to consider. Additionally, rising sea levels. Now, the ice pack that's floating in the oceans is not so much the concern because, as you may know, if you have ice in a glass and if that melts, that doesn't change the water level in your glass. What changes the water level in your glass is if you take ice and add it to the glass, that's going to raise the water level in your glass. And then when that melts, it'll stay at that level. So this is the concern then with global warming, is that it's the surface ice on land masses. So the Antarctic land mass and particularly the Greenland ice pack, as those melt and that floods into the oceans then, that's going to raise sea levels. And as sea levels rise then, we're going to have less land mass. It's going to be extraordinarily expensive, and these are very, very significant. Water supplies. Again, especially in the western United States, it's not talked about much, but this is a real problem. Water's always been a problem for humanity, and it's going to be a huge problem. It's estimated that right now, and this is actually, I think, even a conservative estimate, that Lake Mead will be dry, by 2020 to 2030. And that's a very realistic possibility. So again, water supplies are going to really decrease in the western United States. Also, as global temperature increases, firestorms increase. And this is a positive feedback type of situation. If you look at the western United States, increasing temperatures mean an inability or basically a drying out of vegetation, burning, that releases more carbon. And so we get into this positive feedback. So if you want to look at the primary cause of fires in the western United States, it's tied directly to average temperature. The other aspect of this that's problematic is that as winters get warmer, pine beetles are killing trees because pine beetles that would normally freeze to death in the winter are no longer freezing to death. And so that's killing the pines, and then they are igniting in the summers. And then this is also coupled with deforestation, which would help pull that carbon out of the atmosphere. Another really dangerous and scary thing is methane venting. As I talked about before, as the earth warms, permafrost melts, there are a couple of things that could happen. Growth could increase, but also methane could also be produced by methanogens as they decompose. So this is a major, major concern. And we don't know how much of that will occur. Also, there are large deposits of frozen methane under the ocean surfaces. Those are starting to evaporate, and methane is beginning to vent into the atmosphere. Methane could really tip the scale and run away with warming. And then the thermal conveyor is another concern. The thermal conveyor distributes water throughout the globe. If we have massive melting of the ice pack, that is going to have an effect on this conveyor. And this conveyor is important because it not only distributes temperature globally, but it also distributes nutrients as well. And then again, there will just be extraordinary ecological disruptions that occur. We've already estimated to have lost at least a fifth of our coral reefs. And then also we may be past a tipping point. We don't really know for sure. In my last 30 seconds, I'd first like to congratulate you for making it through what is really a very tough course. And I hope that you will feel confident about your future, because again, if you can make it through this class, I think you can feel confident about any class you're going to face in upper division at the university. I also hope that you feel that you have a better understanding of biology and are going to be able to apply that to your lives. And last but not least, whatever you decide to do in the future, I wish you all the luck in the world.